So the next topic that we will be on, it involves quadratics. Now we are still in with our topic with polynomials, but we need to take polynomials and now go on to quadratics. And this is where it gets kind of rough because we're going to be doing some backwards solving polynomials. So we have learned in recent videos that we've been multiplying using the FOIL method to get a polynomial or trinomial, but now we're going to start working backwards. But what I want us to do is start with our next topic, which is quadratic equations. Now, we're still with polynomials. So let's start with an example, because that's always good to kind of see where this stuff is kind of associated to real life to a certain extent. So our equation is something I want you to kind of understand. Now, our equation, it has something like this. Y equals ax squared plus bx plus c, where a, b, and c are real numbers and a cannot be 0. A cannot be 0. If a was 0, this wouldn't be a quadratic equation anymore. So what I want us to really focus on when we hear the word quadratic, we're thinking about things in the second term. So when you hear quadratic, you're seeing a 2. Now, remember this, just recall, we don't need to put this down, but recall when we did y equals mx plus b. Well, remember what x was? It was our, slope, but there was always a 1 right there. Well, this time, these are not linear. These are not linear. So quadratic equations they're not linear. They're not straight. They're not straight lines anymore. We're going to start doing with non-straight lines. So we're going to look at things like this. That's what we're going to be looking at now. We're no longer going to be looking at straight lines. Okay, so we're changing our viewpoint, our second dimensional. Okay? So that we're looking at those. So, let me give you an example. There's our equation. What does this remind you of, or what does this represent? Let's say you're standing on a building. And you drop a ball or an object. ...240 feet tall, you drop an object. Well, when you drop an object, we have this thing called gravity. And gravity makes things drop to the center of the earth. This formula is actually taking this example into perspective, and we can calculate some numbers. And this is not just used for gravity, there's actually used for financials. This can actually predict lines of best fit for, you're looking at the stock charts. You're looking at, they use this a lot in physics. In physics, where we want to see projectiles, we want to, in economics, we want to see how certain equations will fit to the parabolic curve. But we want to take something like this and we want to see what happens at different spots. So here's what I want us to do. I want to replace this with S of t. Now, you're familiar with f of x. Well, why don't we do that then? Why don't we stick to that? But this time, x is time. So what I want us to do is just to make sure that x, so we're saying let x equals t, or t equals x. Just making sure we're not confusing x's with something else. It's just time, or t. Well, what if I wanted to kind of see what happens when I drop that object at certain times? What would happen at certain times? Can I get a number for those times? And to show you what I mean, I know that's kind of confusing because I haven't really showed you any numbers yet. Let's make a t-chart. So, make a t-chart like this. Put your x, put your f of x, or maybe your equation. And let's get some numbers out of it. So what I did, here's your inputs, here's your equation information, and here's your output. So let's just plug in some numbers. And let's do some calculations. Okay? So let's do some calculations. So, pick some numbers. I want to pick 0. I want to pick 1. And maybe 2. So what this means, this should be seconds. We're going to call this seconds, because it takes time for it to hit the ground. So I'm just going to take 0 and replace it for x. So I'm going to go like this. F of 0, and I will use some different colors for you. You're going to put 0. And we can do the math in here, but I would really like us to just do this fast. So if I put 0 into my equation, wouldn't I get 240? So 240. What if I put 1? So f of 1. Well, isn't that going to be 1 squared, which is negative 16? So negative 16 plus 240. So you should have 224. Let's put 2 in. So f of 2. Do some math. That should be, what do you put 2 in there? That'd be 4. So negative 16 times 4 is negative 64 plus 240, which is 176. And make sure we get our numbers there. Let's plug in 3 seconds. So f 3. We're going to put 3 in there. Was that 9? So that's negative 16 times 9. Just making sure that's 9 because 3 squared is 9. And that's going to be negative 16 times 9. So let's see, negative 16 times 9. And then we're going to make sure we add 240. And we have 96. Do you kind of see what's happening? Do you see what's happening? As the time increases, our distance gets closer and closer and closer to the ground. We're trying to figure out when does it hit the ground. And I want you to kind of look at this. When we plug in 4, it might happen because we're getting so close to the ground and where our numbers are growing. So I'm thinking, without doing any math, my logic is I'm looking at the rates. And I'm thinking, what if I plug in f of 4? What would I get when I put f of 4 into this? And at home, you should be doing the calculations as well. So that's negative 16. 4 squared is 16, which is negative 256 plus 240. And negative 16. Okay. So what I'm trying to show you, at 4 seconds, it's negative. That means at 4 seconds, it's in the ground. It's in the ground. So it didn't actually hit the ground at 4. It maybe hit it probably around 3.7, 3.8, and that's kind of what we're looking at. So is there a way we can do this? Yes, we can plug some more data points in, or when we become better at quadratics, we can actually see a graph and also maybe do some factoring, which is our opposite of FOIL. So what I want us to do is look at a graph. I want to look at a graph. So we do a little graph. So I want us to do a graph like this. Y equals x squared. How would you graph this? Piece of graph paper. Correct? You can put some numbers. Okay, cool. Got the graph done. But what is a graph? What does the graph look like? My guess? Table of values. So pick some numbers. Actually, I'm going to do this way. I want to pick those 5 numbers. And the reason I'm picking those 5 numbers is because, like, first off, I can graph it on my graph. I don't have to make this thing go wider. And also, they're easy numbers. So x squared. So here we go. Isn't this going to be negative 2 squared? Isn't this negative 1 squared? 1 squared? 0 squared? 2 squared? So this is going to be 4, 1, 1, 0, 4. Let's graph them. -2, 4. -2, 4. -1, 1. -1, 1. 1, 1. 1, 1. 0, 0. 2, 4. 2, 4. And connect the dots. This is a special type of functions or special type of graph. So note this is a special type of graph. It is called a parabola. It's called a parabola. So P-A-R-A-B-O-L-A. Parabola. Parabola opening upwards. So this is upward. Upward. This point right here is called the vertex. If it's opening upward, it's the medium or lowest point. Vertex, the medium, lowest point. And that's important because I hope you can see this. You see this line right here? If I took this graph and I folded it along this purple line, it should line up. So that's like taking a piece of paper and folding it along that line. Well, technically, that's what you're doing. This is why this is called the vertex. One other word I want you to know. This line that goes down the middle is called the axis of symmetry. The axis of symmetry. Axis of symmetry. That means that if you fold, it should be the same thing. Okay? So, vertex, axis, parabola, quadratic. 4 terms in this one. But that is with x squared. Our last one what if we wanted a graph, however, we make it negative? What will happen? So here's what I'm going to do. You see the difference? One's positive, one's negative. This is what I'm going to do. Do you see what I did? Okay. I'm just going to plug the same points into both these graphs and see what happens. So if I plug -1 in for x squared, don't you get positive? If you plug 0 in, what do you get? 0. If you plug 1, 1 squared is 1. If you plug 2 in, what do you get? 2 squared is 4. Now, let's go over here. Remember, we still have that negative in front. So we're going to have that parenthesis. If we plug -1 in there, what's -1? What's -1 squared? 1. But -1. If we plug 0 in, well, no surprise there. If we plug 1 in, what do we get? 1, but -1. If we plug 2 in, don't we get 4? But we get -4. So graph this. Okay, let's do some graphing. -1. At -1, you get 1. At 0, you get 0. At 1, you get 1. At 2, you get 4. And remember, it's symmetric. It's axes. That's the first one. -1, -1, -1, -1. 0, 0, no surprise. 1, -1, 1, -1. 2, -4. And it's symmetric. There you go. So this, excuse me, this is red. So the last thing I want you to tell you about this part here is that when you have a negative in front, it goes down. When you don't have when you have a positive, it goes up. So when you have a negative in front, down. Positive in front, up. And this will matter because one last thing. This red one, that point right there is called not the minimum, it's not the lowest point anymore, it's the maximum point. It's the max or maximum. A lot of visuals in here, but it's really taking all the material that we learned and then doing it on something like this. So hopefully that this helped, but we're not done. So maybe I will consider this to be part 1. Yeah, let's use it part 1. These are just parts because there's a lot in these. There's a lot in this. So this is part 1 of quadratics. So I will see you on part 2.